All right, everybody. We'll start it up again. There was a request that tomorrow we don't have a break between the two halftime talks so we can keep the momentum going, so we'll try to adhere to that request. And please, if anybody has any other requests for the third day, just shout it out. Let us know. So without further ado, I'll give the stage to Lucia. Thank you so much.
Hello, so as you probably all know, my name is Lucia. I'm a master's student at University Polytechnica of Bucharest, and I'm here to talk to you about what I've been working on for the past few months, and that's the generic lightweight DRuntime. So let's start with a pop quiz. How many of you know what this code does? Raise your hands. So let me give you a hint. This is an extract from the compiler. Most of the compiler looks like this. OK, so I don't know what this code does. It's meant to be scary. I picked like the ugliest piece I could find. So it doesn't matter. So what if I told you that we could get rid of bits of code like this and also gain a speed up to 30%? What would you say? Woo, that's awesome. So let's see, how are we going to do this? Well, let's look in the compiler and find something strange, something that doesn't occur like normally or usually. It's just some optimizations somebody's inserted in there. Let's just take it and see if we can entirely remove it. Let's lower this optimization to some straight decode, so plain decode in DRuntime. Then remove the code from DMD. No more code there. We are talking about DMD here. And let's refactor DRuntime to do that thing. So why would this be useful? Well, usually because the compiler is difficult, and it's a highly coupled piece of code. It's hard for new developers to understand it and start developing as fast as you do in a runtime library or in Phobos. So this would be one of the main arguments for doing this. Now let's go into a bit more detail. What does DMD do that we can actually replace? Well, there are certain bits of code where DMD takes an instruction, a plain D instruction. Let's take, for example, an array comparison. It just takes this array comparison and it replaces it with a call to a traditional untyped function in the runtime. Well, this happens after the AST is created. It actually happens in the intermediate code generation phase. OK, so it goes that far. And where does this function it calls reside? So it's somewhere in DRuntime in the TypeInfo inheritance chain. So there's TypeInfo, which basically offers runtime information about types. And it implements a couple of functions, such as ordering comparisons and equality comparisons. And that's where the compiler is sending us. So why would this be a problem? Well, I mentioned it's an inheritance chain, so that's object-oriented programming. We have dynamic dispatches for those functions. So if the compiler sends us there, we're going to have to dynamically find out at runtime which of these overrides are we going to actually call. So that's basically a slowdown. So what's the idea to fix this? Well, lowering. We're going to take that code and lower it into a template in DRuntime, so no more dynamic dispatch. And this is going to happen during the semantic analysis phase of the compiler. So when we actually generate the AST, we then go on to analyze it and say, OK, so we have an array comparison instruction. Well, let's replace this with a call instruction to our template. We don't leave it as a comparison instruction and then edit it later on when we are in the intermediate code generation phase. We do it now when we actually semantically analyze the AST. So this is going to reduce the complexity of the compiler. And it's also going to make the runtime nicer. Well, we're going to have some templates there, and it should be nice. But let's talk about this a bit later. But the fact that we implement it in the runtime also offers a major advantage. And that's the fact that the implementation focus shifts to it. So what does this mean? This means that the implementation will be there and most users who want to contribute to the D language can contribute more easily rather than having to do something in the compiler and then a bit in the runtime. It's just going to all be in the runtime. It's going to be a lot easier for new users to join the community. And not to talk about less duplication, safety, and the speed up. So why am I saying that there's duplication? Sorry. Well, it's because the comparison function, for example, implemented in TypeInfo in the runtime, well, for certain types, for example, for doubles and floats, it has the exact same implementation. What's the difference? Well, the difference is that it receives the two arrays as void star arguments, and then on the first two lines, it moves on to casting them, first to a float array and then to a double array. And then the code is exactly the same. So only for those casts, we have two different implementations. Safety, yay. So we're going to have all the errors and type checks done at compile time, and we're going to have errors thrown if there's any problem at all, and speed up. And we're going to talk about this later because we are removing some indirections and we are basically getting rid of dynamic dispatch. So let's see what the process is. As most of you are aware, lowering refers to the following. So we have a bit of code, so two arrays and an ordering comparison. We go in the compiler semantic analysis phase. We lower this to a runtime template. So basically, we generate a call to a function template. And this would be the template. I don't know, do you see the pointer? I'm trying to use it, but OK, so that's the template we are calling. It's pretty straightforward. It has two array arguments. And the code we end up generating is the same if we have here, but instead of a comparison, we have a call to a function. And this would be the function. This is what lowering means, replacing some code with something else, and it's something similar that happens with for each in D. So what are the first steps to actually doing this? Well, we have to identify some actual cases in the compiler where this happens and try to actually implement the refactoring job in the runtime, do the lowering, and so on and so forth. Well, the easiest I could find were array operations. So we have comparisons, ordering comparisons, as I mentioned. We have equals, and then also array assignments, which are a bit more complicated. And then after we have dealt with this, we should evaluate the performance and see if it is worth to continue and do this with all the other things that we find the compiler and could be replaced with templates. So maybe you are not convinced. Maybe we know what to do. We have something to replace. So why would this actually be good? Do we actually need this? Is this worth it? So let's look at DMD and DRuntime on GitHub, as the screenshot was taken, I think, a week ago. So let's look at the pull request number. We have 160 pull requests for DMD and almost 3 times less for DRuntime. That's 69. What do you think about these numbers? Is it that DRuntime has less active contributors? Okay, so those DMD pull requests are not new, and they've not appeared like mushrooms all over the night. So it's because they are there for a very long time, and most developers lack the time or experience to review them, and the development process grows slower, pull requests accumulate. And that's basically because, as I said, the compiler is a highly coupled piece of code. It's very complex, and most developers tend to avoid going into that. So DRuntime is a lot more active. There's pull requests. They get reviewed. New ones are open. So this is actually a problem here, and we are trying to solve it. Then let's move on to the compiler itself. What are we actually going to remove? How are we going to simplify it? So this is the exact piece of code I'm going to remove after array comparisons are finished. So this is the place in the intermediate code generation file where the call to that traditional function is generated. So this code will disappear, and lots of code, other bits of code like this. Okay, that sounds good. Then what about the runtime? How is the runtime going to change after this? So as you can see here, this is the TypeInfo inheritance chain in object.d, which is the main file of from the runtime. And well, as I mentioned, there's a lot of duplicate code there. There's dynamic dispatch all through this inheritance chain, depending on how those classes inherit each other. There's a lot of indirections, and I'll get back to that. And well, we will reduce the use of this if we replace the calls to functions from these classes to actual templates. Most of the uses for this will disappear, and eventually, this is long term, I'm not going to do this, we might even remove the entire chain itself, but that's massive work. It's at the moment beyond the scope of this project. So I said that we are going to do this through templates, so why would that be good? I heard there has been some template bashing at this conference, so I'm not here to say that they are awesome, but in this case, they might actually offer some advantages. So first of all, they are generic. So we're going to have the same implementation for types which share the same implementation. They are compiled when they are necessary. So if we don't need them, we're not going to compile that code. TypeInfo is compiled at the beginning for everybody. So you need it, you don't need it, it's still there. Well, we'll also have richer type information. So if we have traditional functions, those are only going to have the type information you specify next to that function. Well, our templates infer this information. So that's actually awesome. It's something that the current implementation lacks. And also, they are inlineable. Now, it depends on the compiler, of course. I'm not going to say that everything will be in line, but since it's a template, it might be in line, so we are removing the call to it. It's just the code is going to be there directly called. And performance. So what's actually going to increase? Well, I'm going to say that runtime performance. Let's see exactly why. So let's assume we have an array of structs, and this is the struct from the array. It's going to have the comparator operator overridden, sorry. So the compiler in the old approach would generate a call to this function, which is, somebody mentioned it actually, it's add compare to. So we're going to have a call to this, and this, you can see it calls TypeInfo compare of pointers to the two arrays. Okay, so where does this go? We have an array of structs. It goes in the compare function for structs in TypeInfo. And it simply, I think the code is quite small. Do you actually see it? Okay, more or less. So it's just a for loop, and it iterates through all of the elements of the array, and it calls a compare function on something called value. So what is value? Well, value is another TypeInfo. So if we have an array of structs, value is TypeInfo struct. So this is going to send us in the compare function for the struct. So what does this do? We see them, some null checks, something blah, blah, blah. And if this comparator operator is overridden, then we're going to call it. So that's another indirection. So we have a call first to add compare, then a call to the array compare in TypeInfo, then a call to this in the for each loop. Well, those are a lot of calls. So what happens now? The same array of structs. We have this code in DMD, which during the semantic phase lowers our compare expression to the template, and that's it. The template then does the for each. It calls directly the operator which is overloaded, and we got rid of at least two indirections. So that's where the speedup comes from. So, okay, we talked about a lot of advantages, but there are obviously disadvantages. We live in the real world. Not everything is going to be perfect. So the first disadvantage that a lot of people have mentioned is that object.d will get bloated. So all of the information we take from TypeInfo, all those comparison functions which are overridden, are going to end up in templates in object.d. We'll then talk about equals and get hash, which are other functions from TypeInfo. These will also have templates in object.d. So that grows up to a lot of code. Then we talk about all the overloads for these templates we are writing. Overloads for scalar types, non-scalar types. This might actually get out of hand at certain points. So, okay, why don't we factor them out to another file? Well, we could do that. At the moment, these are top-level calls. If we do that, we are going to talk about an import trade-off. We're going to have to import that file before we actually call the function. So this might reduce the performance, and we have to actually see if we do this, will the entire approach be worth it? Then another factor is that we talk about templates. Will the compilation speed actually decrease? Well, it depends how many templates are we talking about. For very simple projects, I have done some tests, and there was no difference in compilation speed, so there's basically nothing we lose at the moment. For larger projects, I don't know. It's up to all of us to actually see if the compilation speed decreases massively. Because basically the templates might end up being compiled several times for several object files or for several types, and this is not really good. Okay, so we've talked a bit about advantages, disadvantages, the approach. So what's actually the current state? What am I actually doing here? Well, compare is finished, array comparison. It's integrated with DMD with the runtime. Equals is still under development, mainly because there are some issues with the DMD tests, so I have some failing. And I've done benchmarks, so let's move on to those. Okay, and this is something I've started, but I had to put them on the back burner because there were a lot of issues. So the benchmarks, as I mentioned. What was the tastiest that I employed? Well, it's simply a function which compares two arrays. And I'm going to have those arrays of different sizes, multiples of 10, and call this function 10,000 times and see how fast that goes. So this is the speedup for array compare. As you can see, for objects, integers, and floats here, well, the speedup is about 1.3 times. So the new code is 1.3 times faster. I think there's a question.
So this is DMD optimization, right?
Yes, this is for DMD alone. Yes. Okay, so one means that there is basically no speed up. And you can see here that we're not losing any performance. We're just gaining slight performance because we removed those indirections in some cases. Now, moving on. This is for structs with the comparison operator overloaded. So it's just the case that I presented to you earlier. And you can see here that we can go up to code which runs 16 times faster. So I think that's actually pretty impressive. It's nice how just removing a couple of indirections and editing the code a bit gains such performance. And the reason why this decreases, I think, is because of my laptop. So it's just, this is the sweet spot for my laptop at 1K elements per array. Okay, so this is basically the speed up for array compare. Moving on to equals. So I said equals is not ready yet, it's not shipped, but I did some benchmarks on my laptop because I know exactly the case that's failing and it didn't really affect the benchmarks themselves. You can see here that the speed up on average is also 1.3 times. We have a bit of a bigger speed up for objects, arrays of objects, so that's almost 3 times faster. For structs with OP equals defined or without it, well, you can see that it's nearly the same performance. We don't really gain anything. It's slightly better for structs with OP equals. And why there is such a big difference between equals and compare is because the compiler did some optimization for equals with this operator overloaded, and apparently now the implementations offer the same advantages. It's not really massively better with templates. Now the surprise with equals was with arrays of integers. So I can't really explain how this goes up to 20 times faster because, well, in the backstage it's still a mem compare. So the old approach and the new approach, they all basically just call mem compare in the background. But in this case, you can see, again, the sweet spot for my laptop, but it is actually an average like 15 times faster, the code with the templates. So again, this is actually quite interesting. For integers, I will still investigate this because I can't really believe my eyes. I ran a test once and it told me that it was 100 times faster, and I thought that was actually a joke. But yeah, these are the results. I ran them several times. So, okay, we have some speed up, but is it actually worth it? Is this code actually used? Because if I improve some code that's not used at all, then that's not literally, it's literally of no use. Well, actually, string and integers comparisons are quite often in user code, and also in, well, basically just any code, your runtime code and Phobos code. A lot of string comparisons occur at compile time. And I know that because when I implemented string comparisons, I ended up, well, with literally loads of errors because I changed something, and then all the places that the compiler would perform string equality comparisons, and I messed them up. Well, they would appear on my bash, and it was not nice. But I could at least see that that code was indeed used, not properly, but it was used. And then we should not forget that the standard library employs a lot of comparisons. So we have algorithms, we have sorting algorithms, we have binary searches. Well, all of them use equality comparison and ordering comparison. So this is actually code that is massively used. Okay, so what's left to do basically? We have to finish equals, have to finish array assignments. So this is something that I'm going to continue with. Then, as I mentioned, I have approached as a first step only array operations. Well, we should have templates and like a homogeneous approach for all the types, either if they are arrays or not. So this should be employed for non-array types as well. And then there's also destructors and switch statements. I haven't really looked into this a lot. This was Andrei's suggestion, but it's something that I will consider in the future. And obviously, code cleanup. I mentioned that I started trying to remove some code, and I was talking about the compare in TypeInfo, but apparently there was some other legacy sort function that was still using them, and I couldn't remove them, but there's an open PR for removing that, and once that's gone, I can move on to removing the compare overrides from TypeInfo. And well, in the end, this project proved that lowering various instructions in the compiler to templates in the runtime can have a lot of advantages. So we are simplifying the compiler. We are removing a lot of obscure optimization sprinkled all over it by lots of people. We are making it clearer, and we are also moving code in the runtime where a lot of people can contribute or, well, I don't know, feel more comfortable contributing. And because we end up compiling we move this implementation to the runtime, we end up compiling with the same language rules, and instead of making the compiler more complicated, we just use what we already have to compile the same code, basically. And obviously the speed up, so we do have faster runtime code, so that's actually awesome. And I think that's it. Thank you.
Thank you, Lucia. We have time for a quick question or two. Walter has a question? That's so weird. It's probably a comment.
Well, not really a question, but an observation. That little piece of compiler code that you showed,
yes,
it was trivially obvious to the most casual observer. Anyhow, I must congratulate you on getting that kind of speed up. That's, you know, when we're talking about speeding things up by 1% here and there is a big deal. To get a 30% on that operation is 30x.
Yeah.
Is very, very nice.
Thank you.
I knew it wasn't going to be a question. Anybody else? Yeah, David?
Just not a question, but a small comment. I think this talk is actually 10 years too late, or 10 years late, because yeah, just a personal comment. Reading the DRuntime code sometimes feels like archaeology. So I mean, it's also sometimes when I was new to D, I thought, well, I was looking for some code examples and thought, how do they do this in the runtime? And then I came across functions like you showed, or several nested functions called foo. And I thought, this may not be this. On one side, this is reference code and production code. On the other hand, it's not exactly a good example how to structure your project. So maybe I'd really like to contribute to what you propose.
Well,
thank you.
Shoot me an email.
Right, so thank you, Lucio. Is there one more?
Did you measure the compilation slowdown of Phobos with this? And also, did you measure the size increase of Phobos?
No, I did not.
Okay. So do you expect a big difference there or not?
Well, for what we have now, so that's array compare and array equals, I don't really expect a lot of bloating or compilation speed decrease. But if we keep adding more templates, then there should be a difference, and it's going to slowly make itself felt.
I didn't mention I'm the student's mentor, so as my mentees, is that the word? I promised them, it is now, starting right 2 seconds ago, 3, 4. They're my mentees, so I promised them air support during their talks. So the question is very topical, and thanks for bringing the point. I do suspect there's going to be a little size increase, but very little. And I think there's going to be no measurable difference in compilation speed because templates are instantiated one per compilation invocation, and Phobos is built package at a time, which means most of Phobos, so there's going to be a few packages in Phobos, and most of Phobos is going to be, remember that long-ass command line, that's, whenever we build Phobos, is going to be that really long command line that's going to happen, which compiles most of Phobos. So it's compiled, for that package, there's going to be one template instantiation per type. So essentially, that's negligible. And of course, compilation package at a time is the recommended way of building D code. Is that right? Okay, thank you. We can take this offline.
So thank you so much, Lucia.
Thank you.
Get one more round of applause. We'll take our last break of the day while we're setting up some furniture on stage for the panel. And please think of some really hardcore grill questions for the three holy spirits that are going to get up, Scott, Andre, and Walter. We'll see you back in a couple minutes.